So welcome everyone. Thank you for being here. This is the first Deeptails Seminar. So this is together we will discuss on how to train your deep multi-object tracker. And so will be Yihong and myself presenting from INRIA. But this is joint work with Alyosha and Laura from Munich, Yutong that is in MIT, and Radu that is with us here at INRIA. So what are these Deeptails? This is the first one, so let me at least explain a little bit what's the idea of this. We all know, probably we are here, that deep learning requires a lot of engineering. So this aims to be a venue in which we can discuss the best engineering practices together with a particular methodology that is also discussed in the seminar. We have this format of, say, not so young researcher that discusses the high-level idea and the methodology, and then a young researcher, typically a PhD or recently graduated PhD, that discusses the details of the engineering details of the deep architecture, which is what we call the Deeptails. So you will have all the information in the web page. You can also find out how to sign up for the mailing list so that you can receive all the announcements. So we will start explaining what is multiple object tracker tracking. So the task of multiple object tracking is given a sequence of images, of RGB images. We have to find the bounding boxes of all the objects in the scene and track them over time. So in this image here, we focus particularly in people, in pedestrians, and the point here is that we have to find the bounding box for each of them, and then track this bounding box over time, and don't switch bounding boxes between people. Right? So traditionally, this has like the deep multi-object trackers are inputting RGB images, and they are outputting bounding boxes. Now, these bounding boxes are compared to the ground truth bounding boxes with the Hungarian algorithm, so as to have an optimal assignment. Once the ground truth bounding boxes are assigned to the estimated bounding boxes, at training time we can compute, for instance, the L2 loss, or it can be any regression loss. And at evaluation time, we will actually compute standard multiple object tracking metrics that will be discussed after. The problem here is that there is a discrepancy between the loss that is used at training, which is the L2, and then the metrics that are used for evaluation. So what we would like to have is a system that is actually approximating these multiple object tracking metrics, and therefore defining multiple object tracking losses, and that then we can use to train our deep multiple object tracker. So here there are two difficulties. First is that the Hungarian algorithm has to be somehow approximated with a differentiable operation. And then we have also to define these multiple object tracking losses that should be a proxy of the multiple object tracking metrics that are not differentiable either. So we will now discuss the more methodological or high-level part, and then I will let Yihong explain the details. So just to be a little bit more in detail on that, once we have the tracking results that are here on the left, we can compute a distance matrix between each of the estimated bounding boxes, each of the tracking results, and each of the ground truth objects. So here you have for each row is an estimated object, and each column is a ground truth object. and each cell in this matrix is the distance between the estimated bounding box and the ground truth bounding box. So now, traditionally, this is fed to the Hungarian algorithm that is outputting an optimal assignment matrix. So you see the matrix on the right is a binary matrix. Now, this is an optimization procedure that has no analytical form, and therefore we cannot have any kind of derivative of this. So then once this is done, as I said, at train time, we can compute the L2 distance, for instance, or any other regression loss. And at test time, we have these two standard measures. There are others, but we will focus on these two. The first one is the multiple object tracking accuracy, MOTA, and or MOT precision. It's the second one. So basically, the first measure, if you don't do any error, you will have 1 or 100%. And then for any false positive, false negative, or identity switch, you subtract from this perfect performance. So I think we all know what are false positive and false negative. What is a bit more particular of multiple object tracking is identity switches. And this happens when a ground truth object that was assigned to a certain track, at a certain frame, it switches to another track. Okay, so the assignment is the assignment operation at time t is reassigning the ground truth object from one track to another, and this is what we call an identity switch. And this, of course, is an error that has to be computed as well. And then for the multiple object tracking precision, well, this is basically the average distance error of those bounding boxes that are assigned to a ground truth object. So as we said, here we have two issues. I mean, it's the same issue, but at two different stages, is that neither the Hungarian algorithm nor the multiple object tracking accuracy and precision have differentiable procedures. So if we want to, so basically the point here is to find a differentiable proxy to this both Hungarian algorithm and MOTA, MOTP. So this is why we propose the Deep Hungarian Network, DHN. There are two conditions that DHN must satisfy. The first one is that it accepts inputs of different sizes because the number of estimated and ground truth objects vary at every frame. People get basically in and out of the field of view. So N and M are dependent on time. So our network has to be able to input matrices of different sizes. The second condition that it must satisfy is that each of the elements of the self-assignment matrix here on the left, on red, so each of these cells of the matrix must have a global receptive field. Why is this? This is because the Hungarian algorithm is a global optimization problem solver. So if we want to approximate, the least we can do is to take decision for every output neuron with taking into account all the input neurons of the distance matrix. Okay, so each element of the output must have a global receptive field. So at the end, what we did is that we combined different flattening operations with sequence-to-sequence bidirectional recurrent neural networks in this way. So we first have a row-wise flatten, a BRNN, and then we have a column-wise flatten, again a BRNN, and then we are able to output a soft assignment matrix. So in this way, we are sure that all the output pixels have seen all the input pixels, and that we can have a variable time-varying matrix size. That's for the first part, and the second part is a little bit more tedious. It's about approximating MOTA and MOTP. So we need to basically approximate counting operations for the false positive, false negative, and identity switches. And we do that by basically taking the soft assignment matrix that is output of the Deep Hungarian Net. In case of the false positive, we will add a constant column and then apply row-wise softmax. So for instance, we see that the first two rows the assignment was already performed. Instead, it was 09 and 08. And when we apply softmax, this doesn't change much. But for the last row, it was a very loose assignment. Then when we apply softmax, basically what happens is that we have this 08 on the bottom right, and this means, so we interpret this that the probability of this estimated track to be a false positive is actually 08. So basically, when we sum over this column, this yellow column here, we get the expected number of false positive at time t. To compute the false negative, we will use the same principle, but let's say column-wise. So here, when we sum the elements of this row on the right, of this yellow row, we get an estimate number of the false positive, the false negative. Sorry. The identity switches are use the matrix that was computed column-wise with a column-wise softmax, but it is masked by the previous assignments. So I mean the assignments that were done at time t-1 at the previous frame. Okay. So basically here, if the assignments are shown in red, and the not assignments at the previous time frame are shown in blue, and what we are going to do is take the current matrix CC, mask it with the blue, and then sum all over the blue squares. And now here it becomes very clear that at the previous time frame, the second object xt-1, 2 was assigned to the first ground truth object, but at this current frame, it is assigned to the second object, not to the first, and therefore this is an identity switch. Okay, so the sum over these blue squares is expected number of identity switches. Now we are left only with the multiple object tracking precision, which is very easy. It's basically we use the Sear matrix to create a mask, and we apply this mask to the distance matrix, and we obtain here an estimate of the multiple object tracking precision. So how will this work? So in a first step, we will train the Deep Hungarian network, and Yihong will explain that. Once this Deep Hungarian network is trained, then we will use the Deep Hungarian network. We will fix it, frozen it, and then we will use this DHN with the MOT laws to train a deep multi-object tracker. Then at test time, we are using the multiple object tracking metrics, the standard ones. Okay, so this is of course the standard protocol. We are not changing this, but at least at training time, we are using a differentiable approximation of the MOT metrics for training. So here are some examples of what happens. These were supposed to be arrows, these red things on the images. I don't know why we don't see it very well. Basically, here we wanted to show some examples on when our losses are helpful. So you can see the original method was tractor, and then ours is tractor trained with our DeepMOT framework. And you can see here that the original tractor had some identity switches on the first row, okay, and that we are able to correct this thanks to our loss. And it happens the same here on the bottom images with false negatives on the left and false positives on the right. When we compare this to the state of the art, we can see that using DeepMOT is improving the performance of tractor. So we are able to reduce false positives, to reduce false negatives, to reduce the number of identity switches. And overall, we are able to improve the performance and therefore set a new baseline for the state of the art. So I will let now Yihong present the Deeptails.
Yeah, thanks, Xavier. So in the following slides, we will go into the implementation details of DeepMOT. Okay, let's first recall at each training iteration how a deep multi-object tracker is trained. So during training, the Deep multi-object tracker takes RGB images as inputs, and it will output predicted bounding boxes for each object in the image. And during training, we have the ground truth bounding boxes. So we can calculate the distance matrix between the ground truth bounding boxes and the predicted bounding boxes. And this is served as the inputs for DHN. Then the DHN will output a soft assignment matrix. After that, by using the soft assignment matrix and the input distance matrix, we can calculate the DeepMOT loss, as Xavier said. The gradients from the loss, from the DeepMOT loss, will be backpropagated through the DHN, and finally arrived in Deep multi-object tracker, and we will update the weights of the Deep multi-object tracker. So first of all, I will discuss how distance matrix is calculated. This is useful for both DHN training as input, and also for the training of Deep multi-object tracker. We call it here DeepMOT training. And after that, before training the Deep multi-object tracker, we need first to train the Deep Hungarian network, DHN. I will detail more in the following slides. And after the DHN is trained, we fix the weight of DHN, and we go into the DeepMOT training. So first, we described here how a distance matrix is calculated. In the community, we use a lot of IOU to calculate the distance between two bounding boxes. Like in this example, the green one is the ground truth bounding box, and these two purple one or blue ones, they are predicted bounding boxes in the case of DeepMOT training, or the noisy detections in the case of DHN data preparation. So we can see the IOU between them and the ground truth box are 0. So if we use it, use IOU alone as a distance matrix, then in this case, we will not have gradient to update the Deep multi-object tracker. For this reason, we add another distance, which is normalized and rescaled center point L2 loss. And the normalized L2 loss is calculated by dividing the L2 distance dividing the L2 distance by the square of image height and image weight. But using this normalized L2 loss, there's a problem, is that the normalized L2 loss will be smaller than 1 minus IOU distance. As we can see in this plot, the red one is 1 minus IOU, and the green one is the normalized L2 distance, center point L2 distance. So we add exponential term to rescale this green curve and make it the difference between the L2 distance and 1 minus IOU to be smaller. As we can see, the rescale L2 loss is closer to 1 minus IOU. And we just calculate the mean between this distance as the final distance for calculating the distance matrix. Yep. Also, this is for calculating the appearance distance. So the Deep multi-object track we have tested on several multi-object tracker. 2 single object tracker used as multi-object tracker, and the other one is the state-of-the-art multi-object tracker, which is called Tractor, like in this figure. But in the original implementation of Tracker, they don't have ReID head. They use an external ReID network to do the reality part. But here we just add a reality branch, which is a lightweight reality branch. It's a FC layer with output of 128. So it's really lightweight. And the advantage of our DeepMOT training framework is that we can jointly train the bounding box regression head as well as the reality head. So we need to calculate the appearance distance. So the appearance vectors, they are obtained by performing LU pooling of the corresponding bounding boxes and pass them to the reality branch, and then we get appearance vector. So here we just simply used cosine distance for calculating the appearance distance. And in these slides, I will talk a little bit more about how we generate the DHN data. So for the input data matrices, we use the noisy detection, the distance between the noisy detection and the ground truth bounding boxes, which are provided in the MOT data set. And we calculate the distance between them and generate distance matrix. And to do data augmentation, we also randomly threshold the distance matrix that we generated and threshold them and put the value above the threshold to infinity. So we will not assign, there will be no assignment in this case. Okay, so by doing this, we can double the, we can augment the data by 3 times. And what's more, during DHN training with a probability of 0.5, we randomly permute rows or columns in the distance matrix and its corresponding target assignment matrix. Yes, one more point is that the target assignment matrix is calculated by inputting the distance matrix to the classic Hungarian algorithm to get the ground truth. To summarize, we train DHN as a 2D classification task, and RMS proper optimizer is used. And there is another problem is that the target matrices, they have too many zeros. So 0 means no assignment. So we need to balance a little bit the output labels. So here we just use the number of ones and number of zeros to balance each class. And focal loss is used with a modulating factor of 2. Another point is that, as I said, once the DHN is trained, the weights are fixed during the DeepMOT training for Deep Multi-Object Tracker. Finally, we ablate here different architectures of DHN and compare their performance using the metrics MA, SA, and AA. So first of all, I need to explain a little bit what is MA, SA, and AA. So during evaluation of DHN performance, we can do a hard assignment to the soft assignment matrix because we don't need gradients. Okay. So there are 2 ways to do the hard assignment. One way is to do it in a row-wise, or the other way is to do it in the column-wise. So let's take an example here. In this soft assignment matrix, we look at each row of this matrix. So for example, here, the first row, the maximum value is 0.9, and it is above our threshold that we set to 0.5. So the corresponding position is set to 1. Same for the others, and same for the column-wise maximum, but we look at in the column-wise. Okay, but sometimes in rare cases, DHN will output a wrong soft assignment matrix. That's the errors that we need to evaluate. Like the example here, if we do row-wise maximum soft hard assignment, we can see in the output, in the output matrix, if we look at it in the row-wise, column-wise manner, we can see this blue column, there are more than one assignment. So we count it as several assigned as A. So we count how many columns here that have multiple assignments. And for MA, we just compare each row to the ground truth target. If there's an assignment in the ground truth target in this row, and there's no assignment in this in the predicted hard assigned matrix, then it is a missing assign. So there are two lines that have missing assignments. And also we calculate as a classic classification task, we calculate the accuracy. But as I say, there are too many zeros in the target matrices. We need to balance a little bit the accuracy during the accuracy calculation. The weights are the same as we use in the focal loss function. Okay, here we just present the three different architectures that we ablated in our paper. So the first one is the proposed sequential by DHN. Basically, you just flatten the inputs distance matrix in a row-wise manner and give it to the bi-RNN, and then you get a representation of the distance matrix in the row-wise. And you can flatten this representation in a column-wise and input it to another bi-RNN network. And finally, you will get the final soft assignment matrix. But there is a variant of the DHN network architecture is that we can do things in parallel. So we row-wise flatten and column-wise flatten the distance matrix and input them to two different bi-RNN. And in the output, we concate them before inputting to the FC layers, and we get the soft assignment matrix. Also, in this case, we don't use at all the bi-RNN network, but we use a simple 1D convolution layer. So we do it like a UNet way. We downsample the distance matrix and then upsample the distance matrix, and we get the final soft assignment matrix. So in these two tables, we show the performance in terms of WA, MA, and SA. We can see that the proposed DHN architectures outperforms the others. And one more detail is that instead of using LSTM, we used gated recurrent units, which you will have small gain in terms of performance. Okay, from these slides, we are going to talk about the DeepMOT training, which means that we are going to train the DeepMOT object tracker. So as Xavier said, we need to approximate the FN and FP counting. So we wish to have a value that is close to 1 in this. For example, in this case, there is a FP. We want to have a value that is close to 1 in this cell. So but using the default softmax function with the temperature equals to 1, sometimes there is a problem. For example, in this example, we have a vector of 3 values that they are close to each other. And after the softmax function with temperature equals to 0, we can see the difference between them is minimized. For this reason, we use a temperature which is lower, 0.1. to make the maximum value that we need to be close to 1, as we can see in this example. And as I said, we use a ground truth bounding boxes to train the deep multi-object tracker. And because ground truth bounding boxes, they are perfect, they fit well the objects. So during inference, we don't have the ground truth information. We need to use noisy detections to initialize the track at time t equals 0. To mimic the noisy detection in real world, we add some random noise to the bounding boxes during training. So the first, we randomly shift the bounding box with a probability of 0.4, and we randomly scale the bounding box also. Okay, to summarize, we during training, we initialize tracks with noisy GT boxes at time equals 0. And we let the deep multi-object tracker to predict the bounding boxes for current frames. The tracking lasts for 10 frames, which means that we divided a long sequence into 10 frames per subsequence. And the deep multi-object tracker will output predicted bounding boxes, and we can calculate the distance matrix and put it to DHN. DHN will output the soft assignment matrix. We then can calculate DeepMOT loss. We update the weights of the deep multi-object tracker at each time step. In terms of training time, we need 72 hours to train to the baseline SOTs. But for tractor, because we trained only the regression head and reality head, it takes around 12 hours. So finally, we ablate different terms of DeepMOT loss. In this table, we can see the effect of each term of the DeepMOT loss. For example, if we look at the last 2 rows in this table, without the ID switching loss, the ID switching number of ID switching is higher than the complete DeepMOT loss. So we can see the effect, the ID switching loss can really help reduce the ID switching. And in this table, we just compare our DeepMOT loss with the classic bounding box regression loss, smooth L1. We can see our loss outperforms smooth L1 bounding box regression loss. And another important point is that our DeepMOT loss can jointly train the reality head for deep multi-object tracker, which is not the case in the smooth L1 loss, which can only be used to train the bounding boxes regression. Yeah.
So to conclude and hopefully launch a little bit the discussion. So we have proposed what is a new framework to train the deep multi-object trackers. And to do that, we had to propose approximations for the Hungarian algorithm that we call Deep Hungarian Net, and for the MOT metrics that we call DeepMOT losses. We have provided a detailed description of how did we design the DH-Net and the losses, what are the training and data augmentation strategies, both for DHN and to track a multi-object tracker with the DeepMOT loss. What is maybe the message to take back home is that this combination of DHN and DeepMOT loss allows to backpropagate through the assignment problem. It means that hopefully it's also useful to correct some, let's say, misassignments. And then by doing all this and training tractor with this new framework, we are able to establish a new state-of-the-art baseline on the MOTChallenge datasets. So that was all from us. There are some references here. Before we open the questions, I wanted to thank you, Yihong,
Thank you.
for the presentation and to follow me on this crazy idea.